SpaceX's Starship, the most powerful rocket ever built, is supposed to be the future of orbital payload delivery. It's a titan of engineering, towering over the launch pad, glowing in the sun like a silver arrow pointed toward destiny. It's built to carry astronauts to the moon, to Mars, and beyond. It's built to carry satellites, cargo, and entire modules into low Earth orbit in one shot. But despite all this cutting-edge power and promise, there's one surprisingly stubborn problem. The door won't open. That's right. The payload bay door, arguably the simplest mechanism in the entire mission profile, refuses to budge. How could that possibly be? We're not talking about a minor hiccup. This is a repeated failure. SpaceX has tried not once, not twice, but 3 times to get this door to open in flight, and every single time it's failed. The latest attempt, during the 4th integrated flight test of Starship, was the most promising yet. Booster 14 performed mostly as expected. It completed its separation process and began its return, but things quickly went downhill from there. The booster made an uncontrolled descent back through the atmosphere and exploded at T+616 seconds. That was bad. But worse still, the upper stage, Starship S-25, didn't make it either. It became the 3rd upper stage in the Starship version 2 series to explode in flight. And most notably, during that same flight, the payload door jammed. Again. At the 18-minute mark, the moment we were all waiting for arrived. SpaceX was finally going to demonstrate the Pez Dispenser mechanism for deploying 8 simulated Starlink satellites. It was meant to be a milestone moment, a slick, choreographed release of satellites into orbit. Think of it like dealing cards in a Las Vegas casino, except each card was the size of a washing machine and made of aerospace-grade aluminum. But instead of popping open with cinematic elegance, the door just did nothing. Frozen. Silent. Sealed shut. And this isn't just a cosmetic issue. This failure fundamentally disrupts Starship's future. If it can't deploy payloads, it can't do its job. So why can SpaceX build the largest reusable booster in human history, capable of lifting over 150 tons into orbit, and yet still fail to open a simple hatch? Let's break it down. To understand the root cause, we have to go back to the design differences between the earlier and current versions of Starship. The payload door used in Flight 3, the final version of the older Starship design, was actually more successful. Even though it didn't open completely, it did move. It showed some response. Gave us hope. But the newer version 2 Starship, despite having upgraded components and an all-new payload bay system, actually performed worse. One of the biggest changes was the replacement of the rigid structural bars that reinforced the original payload bay. In version 2, those bars were removed and replaced with a more modular internal piston system. The door now uses internal accessories connected to pistons on either side. These pistons pull the door inward, creating an opening from the inside out, like a trapdoor folding inward. On paper it sounds clever. But in practice, this change seems to have introduced more failure points. If even a single component in the actuator system malfunctions, or worse, freezes due to environmental conditions, the door can jam. And that appears to be exactly what happened. Now let's add a second major problem into the mix: fuel leaks. Elon Musk himself confirmed the issue on X. Starship S-25 suffered a fuel leak during flight. But this wasn't just a minor seepage. During the live stream, you could actually see signs of the leak both inside and outside the ship. It was clear. Ice crystals began to form. Internal fog began to swirl. And then, something really worrying happened. Dense clouds of ice particles began floating inside the payload bay. That shouldn't happen. The inside of the cargo hold should be dry, temperature regulated, and free from debris. These particles weren't just a visual oddity, they were a smoking gun. A clear sign that something had gone very wrong with the ship's internal pressurization. When liquid methane or liquid oxygen leaks in space, it doesn't just evaporate. It flashes into ice and creates pressure imbalances. These changes can introduce mechanical resistance into the most sensitive parts of the spacecraft, especially the payload bay door. If ice built up near the hinges or around the pistons, it could easily block movement. And because the door was designed to pull inward, not swing outward like a hatch, any resistance inside the bay would make movement nearly impossible. But that's just the tip of the iceberg, literally and figuratively. There's another factor that plays a huge role: thermal stress. In low Earth orbit, spacecraft experience extreme temperature variations. One side is bombarded by unfiltered solar radiation, while the other side sits in the icy shadow of Earth. The difference can be over 400 degrees Fahrenheit. This wild temperature swing causes materials to expand and contract. Welded joints shift. Mechanical tolerances change. Pressure seals stretch or loosen. If the door's materials weren't engineered to handle this rapid thermal cycling, warping is almost inevitable. And once a structural surface warps even slightly, doors jam. Actuators bind. Joints seize. All of this makes us question, how reliable are the Starship's welds and seals really? These components are under massive stress, not just from vibration and acceleration during launch, but also from the vacuum of space and the deep cold of orbital night. Even a perfectly engineered system can be compromised by ice, pressure loss, or thermal deformation. So when you put all these problems together, a redesigned door, actuator failures, internal ice buildup, and thermal stress, you start to see why opening a door in space isn't as simple as it sounds. But let's be fair. SpaceX is no stranger to trial and error. That's how they've always worked. Break things, learn fast, and try again. And in this case, we're already seeing signs of how they plan to solve it. The first and most urgent solution is structural reinforcement. The area around the payload bay needs to be rebuilt with stronger support ribs, frames that can absorb stress without bending or flexing during launch or orbital operations. But these supports must be designed carefully. Too rigid and they'll crack under stress. Too flexible and they'll deform under heat. The real goal is to find a Goldilocks zone, a support frame that's strong enough to withstand impacts but light and flexible enough to work with the door's motion system. But mechanical strength isn't the only upgrade needed. The drive system itself, the set of actuators and control pistons that open the door, must be re-engineered. Current systems are too sensitive to pressure loss and ice formation. New designs will need to include built-in thermal regulators, improved seals, and redundant actuators. Think of it like the hydraulic system on an airplane cargo door, but adapted for space and with triple redundancy. No single failure should be able to compromise the system. And there's more. SpaceX may soon return to an older design concept from Starship's early days, the clamshell door. This design opens outward from the centerline like a pair of jaws. It's reminiscent of the Space Shuttle's cargo bay, with two halves that swing open and allow full access to the interior. It's a proven model. It's also less vulnerable to internal freezing, since it opens outward rather than pulling through potentially iced-over interior components. The clamshell door has its own engineering challenges, hinges, locking systems, structural loads, but it's more robust against the kind of problems Starship is currently facing. Now imagine this upgraded system in action. A Starship in orbit with a newly reinforced bay. Sunlight glinting off the silver hull as it glides over the blue curve of Earth. The bay doors open in a clean, sweeping motion, revealing rows of satellites nested in precision-cut trays. Hydraulic arms extend, tilt, and release one payload after another into the void, each one drifting out with perfect timing. It's a ballet in space. And it's the scene SpaceX is working tirelessly to make a reality. But to get there, they'll need more than just better designs. They'll need better simulations, more test flights, and much tighter quality control on welds, seals, and pressurization systems. Every leak needs to be tracked. Every door opening needs to be rehearsed. Because once Starship starts flying critical missions, to deliver Starlink satellites, lunar landers, even humans, failures like this simply can't be tolerated. The margin for error drops to zero. Still, none of this means SpaceX is failing. Quite the opposite. These problems are a sign of progress. You don't discover issues like fuel leaks or payload door jams unless you're actually flying. And flying repeatedly. That's what makes the Starship program unique. Most spacecraft are tested in labs, in wind tunnels, in climate chambers. But SpaceX tests in the real world. With real rockets. With real explosions. And as brutal as that learning curve is, it's the fastest way to evolve. Each failure isn't a setback. It's a blueprint for improvement. So while it might seem absurd that the most powerful rocket in history can't open its own payload door, remember this. The Wright brothers couldn't get their plane off the ground for years. Apollo 1 ended in tragedy. The first Falcon 1 flights all failed. Progress is never linear. But if there's one thing SpaceX has proven, it's that persistence, relentless, obsessive persistence, beats everything. And with that, we move into the next phase of this journey. In Part 2, we'll take a deeper look at how SpaceX is upgrading Starship for future payloads, what the next test flights will involve, and whether Starship is truly on track to become the cornerstone of humanity's space future. Inside the cavernous stainless steel body of Starship, the payload is carefully secured long before launch. It's not simply placed, it's integrated directly into the spacecraft's internal architecture, braced and shielded for the punishing ride to orbit. Once the satellite or other cargo is installed, the clamshell-style payload door is closed and sealed with extreme precision. This clamshell remains shut throughout the chaotic moments of liftoff and ascent, shielding its precious cargo from acoustic shockwaves, atmospheric friction, and the bone-jarring vibrations that rocket engines unleash. But once Starship achieves its target orbit, that's when the real magic begins. The deployment sequence is initiated only after all orbital parameters are verified. A sophisticated, remotely controlled actuator system slowly pries open the clamshell door, revealing the payload to the void of space. What happens next is a choreography of mechanical precision. A central transfer platform, an intermediate mechanism linking the payload to the spacecraft's main body, tilts at a precisely calculated angle, nudging the satellite or cargo into the perfect trajectory for separation. At the critical moment, a dedicated separation system comes alive. This isn't a one-size-fits-all solution, it's tailor-made for each mission, engineered to ensure a clean break and an optimal path for every payload. If there are multiple satellites on board, Starship can even rotate its internal deployment platform, a high-precision turntable designed to adjust positioning mid-orbit. Each satellite is released in a planned sequence, with carefully calculated spacing to avoid collisions or interference. After all payloads are safely away, sensors verify clearance, and only then does the clamshell begin to close, an action that transforms the spacecraft back into its streamlined re-entry shape, ready for the grueling return trip to Earth. But none of that matters if one crucial element fails. And it has, more than once. The payload door on Starship has already proven to be a fragile point in the system. If it sticks, if it jams, if even the tiniest mechanical failure occurs, the entire mission can unravel. And that's just one issue. Fuel leaks, dangerous, volatile, and sometimes fatal, have plagued recent Starship missions, casting a long shadow over otherwise promising flights. 3 recent explosions have painted a grim picture. Starship serial number 33 on Flight 7 exploded 8.5 minutes into its mission, vanishing in a fiery disintegration over the turquoise waters near the Turks and Caicos Islands. Flight 8 was worse. Starship S-34 suffered a sudden and catastrophic loss of control when a signal flare erupted near the tail end, knocking out several Raptor engines. The spacecraft lost attitude, spun helplessly, and eventually went dark. Investigators later confirmed a leak in the fuel system. Then came S-35. It too experienced a fuel tank breach, leading to a drop in internal pressure and a dangerous reduction in fuel flow. Right after separating from Booster 14, subtle signs of leakage became visible near the Raptor 2 engines. At exactly T+8 minutes and 23 seconds, a flare appeared on one of the vacuum Raptors, small but unmistakable. Then at 9 minutes and 36 seconds, a second leak emerged on the exterior hull. It was a haunting echo of previous disasters. These failures aren't just data points, they're mission killers. Each one costs millions of dollars in materials and fuel, but more importantly, they threaten the credibility of the entire Starship program. To fix this, SpaceX engineers are now racing to reinforce the most vulnerable parts of the vehicle. Fuel tanks, engine manifolds, and high-pressure plumbing systems are all being re-evaluated. Secondary protections, tougher alloys, and redundancies are being added layer by layer. But there's another, more futuristic solution on the table. Imagine an intelligent sealing system, one capable of detecting a leak the moment it begins, then responding in real time to stop it before it spreads. It would use advanced sensors to sniff out fuel vapor, temperature changes, or microfractures. It would activate microactuators to close valves, patch surfaces, or even deploy a chemical barrier. Such a system would be incredibly complex. It would require massive resources, thousands of hours of testing, and a complete redesign of several spacecraft subsystems. But if successful, it could revolutionize flight safety, especially for long-duration missions in deep space where repairs are impossible and failure is not an option. Why is all this important? Because this payload door, this simple clamshell, isn't just a piece of hardware. It's a gateway to the future. Starship is poised to become the backbone of satellite deployment for the entire planet. Its design allows it to carry dozens of payloads at once, drastically reducing the cost of space access for companies, governments, and research institutions. One flight could launch dozens of new communication satellites, scientific instruments, or even planetary probes. This scale of efficiency has never existed before. Right now, Starlink satellites are launched aboard the dependable Falcon 9. But the next generation, version 3, is simply too massive for that system. These V3 satellites are heavier, larger, and far more powerful. They're designed to deliver an explosion of data capacity to Starlink's global network, but only Starship has the muscle to carry them. SpaceX plans to launch up to 60 of these next-gen satellites in a single mission, adding a staggering 60 terabits per second of throughput. Each individual V3 satellite will offer 10 times the download capacity and 24 times the upload capacity of the current V2 minis. This isn't a minor upgrade, it's a leap into the next era of global connectivity. And now Starship Flight 10 is waiting in the wings. The vehicle, known as Booster 16, has just completed its full static fire test with all 33 Raptor engines roaring in unison. It's now moved to the production facility for final integration. On this upcoming flight, the payload door and internal deployment system will be tested once more, this time with even more scrutiny. Every mechanical part, every hinge and seal will be under the microscope. The experience gained from Flights 7, 8, and 9 has been carefully analyzed and is already shaping the final adjustments. But let's not sugarcoat it, what happened on S-35 is no joke. When a spacecraft gets to orbit, burns through tons of fuel, survives the chaos of liftoff, and then can't deploy its cargo because a door is jammed, that's not a funny glitch. It's a financial disaster. The cost of that failed mission isn't just the wasted fuel or the wear and tear on reusable components. It's the missed delivery window, the disruption to commercial contracts, and the need to reschedule an entirely new launch. That's hundreds of thousands, even millions, lost in opportunity and reputation. Now imagine that same problem happening repeatedly. A door that won't open. A leak that won't seal. A mission that can't complete. It's enough to double or even triple the real cost of deploying just one payload. That's unacceptable. SpaceX knows it, and they're moving aggressively to make sure it never happens again. And yet, despite all the setbacks, we shouldn't forget where this company came from. SpaceX has a long and glorious record of turning failure into triumph. The early Falcon 1 rockets exploded one after another until, finally, one didn't. Falcon 9 became one of the most reliable rockets in history. And Starship, despite its fiery crashes and stubborn doors, is still rewriting what we thought was possible. So yes, these problems matter. They need solutions, not just patches. But we can be confident that the engineers at SpaceX are not just hoping things work out, they're building the future one fix at a time. And when Flight 10 lifts off carrying S-36, we'll be watching closely. Not for explosions. Not for setbacks. But for the moment that payload door opens smoothly, satellites deploy like clockwork, and a new standard is set, not just for SpaceX but for all of spaceflight.